This lecture is about programming in System F. So we would like to see several examples of writing expressions in System F. The plan is we'd like to translate those examples that we developed for untyped lambda calculus to corresponding expressions in System F. This story makes sense because System F is an extension of untyped lambda calculus with polymorphic types. So let's review the definition of System F. In the case of untyped lambda calculus, we only have expressions, which is comprised of variable, lambda abstraction, and lambda application. In System F, we extend this untyped lambda calculus with basically polymorphic types. That is, we introduce type variables alpha and polymorphic types for all alpha A. So specifically, in System F, we have now types. First, we have this function type, and we have polymorphic types. And in order to express polymorphic types, we have to first introduce type variables like alpha, beta, gamma, etc. And then we have this polymorphic type for all alpha A. And expressions are variables and lambda abstractions. But unlike in untyped lambda calculus where there's no type annotation, here we have type annotation. And we have application. And new to System F is what is called type abstraction, which allows you to introduce new type variables. So in this case, we introduce a fresh type variable alpha. And inside the expression E, we may use references to type variable alpha. And we have corresponding application form, which is called type application. So in this case, we are going to substitute this concrete type A for this type variable alpha. Finally, values are either this ordinary lambda abstraction or this type abstraction. So it turns out that this language, System F, is a direct extension of untyped lambda calculus. Then any expression in untyped lambda calculus perhaps can be mapped to a corresponding expression in System F. But in the previous lecture, we learned that there are expressions in untyped lambda calculus that do not have corresponding expressions in System F. In this lecture, we are going to revisit those examples in untyped lambda calculus, such as Church Boolean or Church numeral, and product type, and how to encode product types and sumtypes and so on in System F. So let's start with the Church Boolean. As we will see later, in the case of untyped lambda calculus, we can definitely encode the Church Boolean, but it's pretty hard to figure out what a given expression really means. So for instance, in the case of untyped lambda calculus, this is the way that we encode Church Boolean truth. This is giving me the first option and giving me the second option, and then I'm going to take the first option. So in this case, perhaps we can easily figure out the intended meaning of this expression from the careful choices of these two variables, T and F. But in many cases, it's very hard to figure out the meaning of a given expression because there is no type information here. But things are very different once we introduce types, because type tells you the intended meaning of the given expression in many cases. So let's take a look at the first example, church Boolean. So this is how we encode church Boolean in untyped lambda calculus. So Boolean false is encoded as given me the first option, given me the second option. Uh-oh. Oh, sorry about this total complete fiasco. So in the case of a Boolean false, it says given me the first option, given me the second option, and we are going to pick up the second option. But there's nothing wrong with these examples, the way that we encode the church Boolean. But it's hard to figure out the key idea behind this church Boolean, the encoding of church Booleans. And the key idea was this: if you have any Boolean value, you can choose one of two options. The first option, usually called T, and the other option called F. And this is the basic idea behind the church Boolean. And there's no way to express this intuition behind the church Boolean in untyped lambda calculus. But with the system F, in system F, with polymorphic types, we can now express the idea behind the church Booleans by exploiting polymorphic types. So how do we do this? So this is untyped lambda calculus, and on this side we are talking about system F. So the church Boolean says, give me two options, and then I'm going to pick up the first one or the second one. So give me two options of the same type. So let's say the first is alpha, and the second is also of type alpha, and then I'm going to pick up one of these two. Because the first option, the second option both have the same type, the choice whichever we make is going to have the same type alpha. So now we start to see that types convey the intended meaning of the encoding. But in this case, we cannot use this random type variable. We have to introduce this type variable explicitly. So therefore, we introduce polymorphic type with this for all quantifier. So this is how we encode church Boolean. So when we talked about church Boolean in untyped lambda calculus, we talked about this idea, but there's no way to express this intuition on church Boolean. We just described verbally, but there was no way to formally express the intuition, the key idea on church Booleans. But now we can because we have types. So just by presenting this encoding, the encoding of church Boolean with this polymorphic type, perhaps we can tell the intended meaning. So now the story is much easier to follow because we have this encoding of type Boolean. Now what is the church Boolean truth? This Boolean truth is going to have this type bool, so it must have this type. So in many cases, it's just a matter of finding an expression of this type. So let's see what that means. So this Boolean true must have this type. So first we have to introduce type abstraction corresponding to this for all alpha. So the first part of Boolean true is this type abstraction, capital lambda alpha. So this is going to have this type. Now you have a function or lambda abstraction whose argument is of this type alpha. So you have lambda t of type alpha. So this is going to have type alpha arrow. And then you have to provide the second option of the same type. So you have a lambda f of type alpha, and this is going to have type alpha arrow. And then you have to return a value of type alpha. But if you think about the type variable alpha, when you reach this point, there are only two expressions, two distinct expressions that can have a type alpha, namely t and f, and nothing else. You cannot find some other expression or value of type alpha, because nothing is known about this type variable alpha, and when you reach this point, you have only two concrete expressions of type alpha, namely t and f, and nothing else. So if you'd like to build an expression of type alpha here, there are only two choices to choose from, which is either t or f. And in the case of Boolean true, we choose the first option. And this is a very important point. The point is, you introduce a fresh type variable alpha, and we know nothing about this type variable alpha. So at this point, we don't have any expression of type alpha. And later we introduce this formal argument, this variable t of type alpha. And at this point, now we have the first expression that can be assigned to type alpha. And here we introduce another expression of type alpha. So when you reach this point, you have only two choices, either t or f. And in the case of Boolean false, encoding goes almost the same, except the last expression, which is f. So as I said before, the exercise is just straightforward. You are trying to find an expression of given type, and then you are naturally led to the discovery of the expression of the type, the given type. So this is how we encode the church Boolean in system F. And the encoding here is perhaps hopefully more readable than the encoding in untyped lambda calculus. Next, let's see the church numeral. Church numeral. So the idea behind the church numeral is the goal is we would like to encode natural number n. So let me write n with a hat. This is going to be an expression in untyped lambda calculus or in system F. And the idea is the inherent capability of a natural number n is the ability to count something exactly n times. So for instance, if you have natural number 3, its inherent capability is to be able to count something 3 times, 1, 2, 3, 3 times exactly. And in the realm of lambda calculus, the only thing that you can actually count is, if you think about the way that lambda calculus is defined, the only thing that we can count is actually function applications. Then there's nothing else. So then this natural number 3 is going to be encoded as a function which takes another function f and then returns the composition of the function f 3 times. So this is how we encode natural number 3. So this is the notation for f raised to the power of 3, or f to 3, f composed 3 times. That is f composed with f composed with f. So that's the idea. And this natural number n we've encoded as a function, a higher order function, which takes function f, and it returns f composed n times. Now, that's pretty much the idea, the essence of a Church numeral. But it's very hard to read expressions denoting Church numerals. So for instance, one is lambda f dot f1, and f1 is f composed only once, so it's the same as f itself. So it's an identity function. And it's unclear if this identity function was intended as encoding natural number 1, or if this is equivalent to lambda x dot x. And it's unclear if this expression was really intended as an identity function. It's unclear from the context. So now let's rewrite these Church numerals in system F. First, we notice that we are going to compose the same function several times. That is, we compose the same function f with itself. This means that the domain of this function f, let's say this function f takes a domain of type alpha and returns a range of type beta, then it's going to compose the same function again. This beta is now going to be alpha, which means that this function f must be mapping from the same set to a set to the same set. So in other words, if we assign a type to this function f, it must have this form. You can't have something like f int arrow bool, and you cannot complete the composition of the function f. So the bottom line is, because we are going to compose the same function several times, so here, because we are going to compose the same function several times, the domain and the range of this function must be identical. So all I'm saying is that if we were to assign a type to this function f, this function would have something like a arrow a. So this is what is new in the encoding of Church numeral in system f, because now we have to deal with the types. So let's translate the Church numerals from untitled lambda calculus to system f. Let's start with the type. So what is the key idea? So this is the type for natural numbers in system f. So how do we encode this type nat? So this is a type, and we'd like to encode this type nat in terms of function type and type variable and polymorphic type. How to encode? So the inherent capability of natural number is to compose the function several times. So perhaps it's going to take a function and returns another function. But the thing is, as we have seen in this example, this function that we are going to compose several times must use the same type for both domain and the range. So let's say the domain has a type alpha, and the range must have the same type alpha. And we are going to compose this function several times. So if we compose this function twice, then we have alpha arrow alpha, and then this one is applied to the same function. So in the end, we are going to generate a new function of the same type. So this is the source function, the function given as an argument, and this is the result of composing this function. So this is the basic idea on encoding Church numerals, how to encode the natural numbers in system F. But we cannot use an arbitrary type variable alpha here, so you have to explicitly introduce it. using this all alpha. So type net can be encoded as this polymorphic type. Now it's much easier to see what is going on in the encoding of church numerals just by looking at this one. And if you think about the meaning of this type, actually the only way to interpret meaningfully this type is this is a given function and this is the result of composing this function either 0 times, once or twice, or a certain number of times. So this is a very important thing about polymorphic types. This is the only meaningful interpretation of this type, and there's no other meaningful interpretation other than this one. So now we can express the idea on church numerals with this type, which is a huge advance over the encoding in untyped lambda calculus, where everything was uncertain. For example, is this intended as the encoding of natural number 1, or is this intended as just an identity function? So it's unclear. Now, thanks to this encoding of type, the encoding at the level of types, now we have a much better chance of figuring out the intended meaning of the given expression, unlike in untyped lambda calculus. Now, let's encode church numeral 0. Similarly to the church Boolean examples, the exercise is usually finding out an expression of this type. So 0 has a type net, so it must have this polymorphic type. So the first part of this expression is definitely this capital lambda elf, where we introduce this polymorphic type. And then we have to build a function of this type. So we have first lambda f of type alpha arrow alpha. So this is given as an argument. Now the remaining job is to construct a function of this type alpha arrow alpha. So let's build such a function. So the argument is x of type alpha. Oh, sorry, this is not arrow, this is a dot. And the remaining job is to find an expression of type alpha. Then this expression is going to have this type net. But this 0 is the result of applying the function f 0 times, which is tantamount to saying that not applying. So in other words, if we say we apply the function f 0 times, it means that we do not apply the function. So this is the argument, and we do not apply the function f, so we just return x. The encoding of 0. Now things are very clear because this argument is given this function type. So contrast the encoding of 0 to the same encoding in untyped lambda calculus, which gives you just lambda f, lambda x, and x. So it's hard to tell what is the intended meaning of this expression. Now things are much easier to figure out thanks to the use of types, these polymorphic types. All right, so next, how do we encode successor? So successor is going to have type net arrow net. So for instance, if this function successor is given, say, an encoding of a natural number n, is going to return n plus 1, the encoding of n plus 1. So let's figure out how to construct such an expression. The successor is, first of all, it must be lambda abstraction because it has a something, arrow something, and the first something is net, so x has a type net. Now, we are supposed to build an expression of type net, and net is encoded as this polymorphic type. So this is going to have type for alpha, alpha arrow alpha, arrow alpha arrow alpha. So the first part of this expression is capital lambda alpha. So we have introduced this polymorphic type variable alpha. And then the next part is this function f of type alpha arrow alpha. And finally, we have to build a function of this type alpha arrow alpha. So give me an argument x of a type alpha, and finally the remaining job is to find an expression of a type alpha here. Now how do we build an expression of type alpha? Because we are constructing this successor function, we have to apply the function f x plus 1 times. So we are going to apply the function f x1 plus times, where the argument is this variable x. So first we have to somehow exploit the argument x here, because this is confusing. Let me call it y. Okay, let's say this is x. So this is x, and the inherent capability of a natural number is to count something exactly x times, or a given number of times. So x has a type net, and let me expand the net to polymorphic type, which is this one. So let me copy it over here for alpha, alpha arrow alpha, alpha arrow alpha. Now we'd like to apply this expression f to function f, so that we can have f applied to x times. So where x is encoding of, if x is encoding of say 3, then this is going to be 3, for example. F composed 3 times. Then first you have to get rid of this for all. So therefore what we do is we build a type abstraction. So x is this polymorphic type, and f has a type alpha arrow alpha. So therefore we apply this x to alpha. So if this is confusing, the student can replace this one as beta here. Beta, 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 beta. And there's no difference between this one and this one, because you can apply alpha conversion. So x is this polymorphic type. Now x applied to type alpha as alpha arrow alpha, arrow alpha arrow alpha. Now we are ready to apply this expression to function f. That is, f has type alpha arrow alpha here. F has type alpha arrow alpha, and x applied to alpha has this type. Then from these two, you have x applied to alpha applied to f has a type alpha arrow alpha. So this one comes from here. And this is perhaps the f composed of, for instance, 3 times. if X is encoding church number 3. So we have X alpha F. And what is the type of this expression? So this expression has a type alpha arrow alpha. And we have applied the function f x times, or the number of times as encoded by this expression x. But we are trying to build this successor function. So now we have to apply the function f one more time. So a trick here is you just apply this function to this argument f of x. Or actually, this f of y. This is y. So f has a type alpha arrow alpha, and y has type alpha. So therefore, fy has type alpha. So we use this expression here. This one has a type alpha, so the whole expression has this type alpha. So this one type text. Everything is fine. This one has a type alpha. So this is how we implement the successor function in system F. So notice that throughout the construction of this expression, we tried to make a good use of types. So the types were guiding the construction of the whole expression. We just tried to find an expression of a given type. So for instance, here we tried to find an expression of a type alpha. So this is how we encode successor and zero and natural number. So if you compare these expressions with those corresponding expressions in untitled lambda calculus, we immediately realize the power of types. Types help you a lot to figure out the meaning of the given expression, the intended meaning of the given expression. Now, let's talk about product type. The system F does not have product types, but we can definitely encode these product types by exploiting polymorphic types. How do we encode this product type? So the idea behind the product type is, well, we already discussed the idea on encoding product types, but there was no way to express this idea with the types in untitled lambda calculus. Well, because we didn't have types. But in system F, we have types. Now we can express the idea on this product type using polymorphic types. But the idea was, if you have a value of this product type A times B, you have both A and B. But you don't have this product type, so you have to somehow express the fact that you have both A and B indirectly. And the way we do that is, there's a client here. Client tells you what to do with A and B with the function A arrow B arrow alpha. So this client tells you, well, you have both A and B, so apply this function to what you have, and then produce alpha, and then return the results back to me. So that's the idea. So what that means is that give me a function that consumes both A and B, and then I will apply this function to A and B, which I am supposed to own. So I definitely have both A and B. So you just give me a function of this type, and then I will produce alpha for you. So that's the idea behind product types, how to encode the product types. Now, this idea becomes concrete at the level of types. This alpha is not given for free, so you have to introduce this type variable alpha. So finally, we have this encoding. So we can express the idea on encoding product type at the level of types here in system F. And this also reminds us of the equivalence between those two functions, say a times b arrow c and a arrow b arrow c. So we learned that these two types are equivalent by curring and uncurring. There's no difference, and we can even explain the equivalence in the logical terms. This one says, if you have A and B, then I can produce a C. And this one says, if you can provide A and then you can provide the B, then I can produce a C. And if you think about the interpretation, these interpretations carefully, then you will realize that the two statements are just indistinguishable. They are logically equivalent. So we see here that there's something similar. Something similar is going on. This product type is indirectly expressed in terms of this curried function. So this is how we encode product type in system F. Now let's complete the encoding of product type with the constructs for product type. The first is a pair, and the second is first this projection term. Second. So what is the type of pair? Pair is you give two components alpha and beta, then I will produce a pair of these two components. So that's the type of pair. But these type variables are not given for free, so you have to introduce these type variables yourself. So you have for all alpha, for all beta. So it says, for any type alpha and for any type beta, give me a value of type alpha and another value of type beta, then I will construct a pair for you by pairing them up. Then what is the expression? And similarly to the previous examples, it's just a matter of finding an expression of this type. So first you have for alpha, so you have to introduce this type abstraction. And similarly here, type abstraction. Now you have this function. So first, let's just say the first argument is x of type alpha. The second argument is y of type beta. Now you are supposed to build an expression of type alpha times beta. Then according to this encoding, this expanded to, let's use gamma here. For all gamma, alpha arrow, beta arrow, gamma arrow, gamma. That is, you have to build an expression of this type, which expanded to this one. So, how to do this? You have for all gamma, so you have type abstraction lambda, capital lambda gamma, and then you have function f of type alpha arrow, beta arrow, gamma. And now you have to find an expression of type gamma. How do we do this? Well, you have a function f of this type, you have a value of type alpha, you have a value of type beta. So it's just a matter of applying f to x and y. and this guy has a type gamma, and that's it. So this is how we implement the pair. What about first? First it has this type. For all alpha, for all beta, if you give me a product of type alpha times beta, then I will extract the first component, which is alpha. So first has this type. And how do we implement the first? Again, it is a simple exercise in which you are trying to build an expression of a given type, this one. So you start with capital lambda alpha. For this one, you have to introduce capital lambda beta. And you have an argument of this type, lambda x of type alpha times beta. And now you have to build an expression of type alpha. And this alpha times beta expanded to, according to this definition, you can rewrite it as for all gamma, alpha arrow, beta arrow, gamma arrow, gamma. Then how do we build an expression of type alpha? So this is going to be alpha. So this is going to be gamma is going to be alpha. So therefore, you have to first instantiate the gamma to alpha. All right. So what that means is that this one has a type. X has a type alpha times beta. So X applied to alpha has a type alpha arrow, beta arrow, alpha arrow, alpha. Now it's just a matter of finding an expression here of type alpha arrow, beta arrow, alpha. Then this expression has this type, and this expression has this type. So therefore, the whole expression is going to have this type. Then how do we construct an expression of this type? It is take the first choice, take the second choice, and just return the first choice, just like a Boolean truth. So it has given me the first choice, t of alpha, given me the second choice, f of beta, and then return t. Then the whole expression has a type alpha. And the case for the projection second is completely analogous. As the last example, let's talk about this sum type. In this case, we just show how to encode the sum type a plus b, sum type a and b. And the idea is, if you have a value of type a plus b, sum type a plus b, you have either a or b, but you don't know which. So the only way to make a product use of this value is you give me a function of type a arrow alpha, which specifies how to consume a value of type a. In the case that what you have is indeed a value of type a. But that's not enough because you may happen to have a value of type b. So to provide for this case, you have to give me another function, b arrow alpha. And this function will be used when you have a value of type b. So you have either a or b, but you don't know which. So to provide for the two cases, you have to give a function of type a arrow alpha and another function of b arrow alpha. And then whichever of a and b you have, you can always produce value of type alpha. That's the idea behind the sum type, how to encode the sum type. So it's going to be encoded as a arrow alpha B arrow alpha, arrow alpha. But this is not given in advance, so you have to explicitly introduce this for alpha. So this is how we encode some type. Then how do we, what's the type of injection left? Injection left would be for all alpha, for all beta, give me a value of alpha, and then I will construct a value of this some type, alpha plus beta. And injection right is completely similar. And what about case? If you have alpha plus beta some type, then in order to use this value of some type, you have to provide two functions. What to do when you have value of type alpha. And you have to also tell me what to do when you have beta. And if these two functions have the same return type, then whichever is the case, you can always produce value of type gamma. And finally, these type variables are not given in advance, so you have to introduce them explicitly. So this is how we encode the constructor for some types. So as we have seen in all these examples, superficially system have the type in system F is just function type, polymorphic type, type variable, and polymorphic type. So it appears like a system F doesn't have this capability of encoding product type and some type. But that's not the case. We can encode all these product types and some types and Church Booleans and numerals by composing these polymorphic types and type variables. So this is how we encode all these familiar constructs. And also, it is partially the evidence that system F is really rich in its expressivity.